Welcome back, everybody. Even the best mechanics operating the most accurate machine tool is not able to produce a part as precisely and accurately as specified on a drawing. For this reason, it is necessary to apply tolerances when dimensioning parts. A tolerance is a total amount of variation permitted from the design size of a part. A basic rules of thumb when applying tolerances is to make them as large as possible and still be able to produce a usable part. So tolerance is the amount of variation permitted in design of the part. Tolerance expressed in limit plus and minus 0.002. That means the acceptable error is going to be either plus 0.002 or 0.00 or less than 0.002. Design size is nominal size from which tolerance size are calculated. Sometimes only one limit is given. So either the error cannot be greater than 0.002 or and it's not greater than 0.003. The design size followed by the tolerance 12.382 plus and minus 0.003. The design size of the part is also known as the nominal size. This is the dimension from which the limit are calculated. For example, given this value here 12.382, that means the acceptable tolerance is plus or minus 0.003. That means if you come up with a little bit, let's say 12.379, and your product still be acceptable. However, if it's greater than this tolerance, that means your product may not be acceptable. So you have to clearly word the notes so only one interpretation is possible. Orientation should be horizontal, and general notes should be above the title block. Detail notes should be as close to the reference point as possible. Add notes after all dimensioning is done. Very important thing. For example, how we're gonna define the shelf limit. So the shelf limit, given that whatever the dimension of the shelf, and then the tolerance is plus or minus 0.010. With that acceptable tolerances plus and minus 0.010, you can just subtract from the dimension. Subtract that with 0.01 to get the upper limit, and add 0.01 to add 0.01 to get the upper limit, and subtract 0.01 to get the lower limit. So for the hole, for this example, if the hole is diameter is 0.525, the tolerance, the acceptable tolerance, plus or minus 0.010. That means for upper limit, you can add 0.01 onto this diameter of the circle. That's give you 0.535. That's your upper limit. And your lower limit is 0.515 by subtracting 0.1 from 0.525. The key term we have is allowance, clearance fit, when the space remain after the part are joined, interference fit, transition fit. So we have a few key terms how to define this tolerancing. So for the actual size, also called the product size, this is the actual size of the product after it is produced. Allowance, the amount of room between two main parts, usually considered the tightest possible fit between the two parts, is called the allowance. So the tightest possible fit between the two parts is called the allowance. So we have other term like bilateral tolerance. A bilateral tolerance is one in which variation from the nominal dimension is allowed in both the plus and the minus direction. 0.50 plus and minus 0.002, one of the example to show the bilateral tolerance. Datum is, here's the datum, and is for the reference the location, and a theoretically perfect surface, plane, axis, center plane, or point from which dimension for related feature are established. So the limit, the largest and the smallest possible size in which a part may be produced and still be usable. The limits are calculated by applying the specified tolerance to the nominal dimension. And least material condition LMC, the condition that exists when the least material is available for the feature being dimensioned. Least material condition, abbreviated with LMC, is the lowest limit for an external feature and the upper limit for an internal feature. So if you look at the next one, you can see some of this good example there. And maximum material condition MMC, the condition of part in which the most material is present. Maximum material condition MMC is the upper limit for an external feature and the lower limit for an internal feature. Nominal dimension. This is the dimension from which the limits are calculated by applying the specific tolerance to the nominal dimension. One can calculate the upper and lower limits. Tolerance, the total permissible variation in size for a part. The tolerance is the difference between the upper and lower limit for a part. Unilateral tolerance, a tolerance that may vary in only one direction, either in the plus or minus direction, but not both. So it's either or, but it's not both. In addition to this tolerance-related definition, engineers should also be familiar with the type of fits that are used with the mating part. The following definition relates specifically to fit between mating part. So let me summarize this. The abbreviation: maximum material condition MMC, least material condition LMC, and we have in addition to this tolerance related definition, so we should familiar with the type that what kind of fit we have. We have tolerance. We just talk about unilateral tolerance, and we have all this datum, limit, and bilateral tolerance. And now we want to talk about how to describe the how fit the object is going to be. We have an allowance fit. The allowance fit is similar to the tolerance, and just to show how tight you want your object to be, is allowable fit. So that means if you given this limit here, and the hole is 0.515, and the MMC shelf is 0.510, therefore the allowance, the tightest fit you can go is 0.005. That's the allowance fit. That means if it's not within this allowance, and it's not gonna, this object here is not, this shaft is not gonna fit into this hole. Same thing applies to this current fit. A current fit is one in which there is a space remaining after mating part has been assembled. To determine the current fit, the current fit is based on the least amount of material. The least material condition is 0.52535, and then you have 0.490 for the shaft. The difference is 0.045 currents. That means the loosest fit you can get. This is the loosest you can get. Currents is the loosest. Allowance is the tightest fit you can allow them to manufacture. So if you look at the next example, the smallest shaft in this example is larger than the largest corresponding hole. To determine the amount of interference, you can calculate the allowance fit. So the interference fit is given the 0.501 maximum material condition, and then for the hole you have 0.494, and the allowance, the tightest fit is, subtract that, give you 0.007. For the currents is 0.5 minus 0.496. Let's give you 0.004. The currents, the currents for this shaft to be inserted into this hole. So with that allowance 0.07, if it's greater than 0.7, it's not gonna be, you're not gonna fit in. So this is the tightest you can fit in 0.07, but then the smaller the maximum material condition is, then it's gonna be the loosest you can go. So the allowable currents for this particular case is gonna be between 0.07 and 0.04. If it's too loose, it's not gonna fit in. If it's too tight, it's not gonna fit in. So in this example, there can be both a current fit and an interference fit. The largest shaft in this example would interfere with the smallest hole. However, the smallest shaft will fit through the largest hole. This condition is illustrated in the calculation. So what it is that, this thing here, you can see the tightest you can fit is 0.01. If it's greater than this differences, let's say if this is happen to be 0.002, this may not fit in because the tightest fit is only allow you to can have like 0.01. If this shaft is 0.5 and the hole is 0.499, this shaft can insert into the hole very tight. You have to kind of squeeze them in. But if this shaft happen to be 0.501, then I don't think you can fit it into the hole. So that's the point. So you want to see how loosest you can go, the most you can do is 0.07. Subtract 0.02 from, subtract 0.496 from 0.502, and the clearance, the loosest fit is 0.007. If greater than 0.00, let's say 0.008, if the difference between these two numbers is 0.008, then it's way too loose. So we don't want to go, it's not allowable to have too loose of the shaft, or it's too tight to the shaft. Size limit. The concept of size limit, the cylindrical part shown in this figure will be useful if produced at any size between the upper and lower length limit, and at any diameter between the upper and lower limit inclusive. Cut down on waste, require less time to produce the part, and therefore cut the cost of the production and corresponding cost of the part. So the concept of the size limit is to make sure that you don't want to make it too. If you don't specify that, it could waste a lot of your time and money and also material. So the best thing is to make sure that this size fit. You have to determine all the size fit to make sure that the designer or the manufacturer won't design something that is greater than your allowable size limits. Design size. Design size is another way of stating nominal size. The design size represents the idea of the engineer is seeking. Ideally, the produced size will match the design size. The produced size will match the design size. However, since this is not practical, tolerances are not normally applied. With that, we're going to continue on with maximum and minimum size in the next video.